Good afternoon. So today we're going to go over an important lesson. May take a while. It's important because if you understand it very well, you will have an easier time on the second half of the course. We will deal for the first time in this class with the notion of infinity in the context of integrals. Part of the problem why the infinite series, which is the second half of the course, looks or seems difficult to many students, is because the students usually don't have a habit of thinking via definitions. Notions like infinite sums or infinite domains or in general anything related to infinity are vague for good reasons. They mean nothing unless you actually define them in a precise way. Because the word infinity is used in very different contexts and can mean completely different things. So this is the first lesson in which you really have to make sure you understand the definition of the concept. And then when the problem is supposed to be solved, related to this section, you have to go through that definition, not through any feeling you may have or intuition you may have at the moment. So with practice your intuition will be the correct one, but that will be formed via practice based on precise definitions. So without further ado, let's go over some preliminary stuff before we get into the main topic. This notion of an improper integral actually deals with two types of integrals, and the first one is one in which the interval of integration is of infinite length. So let me give you two examples. So let's write this motivation, so to speak, before we get into the actual definition. So I'm going to look at two functions side by side. So let's say I'm looking at f of x equals 1 over x squared and g of x equals 1 over x. And I'm going to take both of these functions to be defined on 1 infinity. So for x greater than or equal to 1. In other words, the domain, I restrict the domain of definition for these functions to 1 in infinity. They are defined for any real number except 0, but let's look at the domain from 1 to infinity. And I'm going to sketch these functions in the same coordinate system. So because they start from 1, right? If x equals 1, the starting point for both functions is actually 1, 1. So let's say this is 1, 1. This is a common point to both of them. And the functions are decreasing. So the first, and let's say 1 over x is this. Both of them have y equals 0, y equals 0 as a horizontal asymptote. So let's write it down here. Y equals 0 is a horizontal asymptote for both. Okay, so this is y equals 1 over x. And it should be pretty obvious that because you have 1 over x squared, right? So this is g of x, the first one I sketched here. The second function will decrease faster. So the second function will go down faster towards 0. Okay, so let's say this is y equals 1 over x squared, or f of x. All right, so what if I ask, what is the area between the graph of each of these functions and the x-axis over its domain, of course. So for example, for the function g of x, for 1 over x that sits on top of it, the area, it's basically a shape that is never closed, right? Although because the function approaches 0, but it never actually touches the x-axis. So the shape that I'm trying to compute its area, if I were to sketch it separately here, in both cases it looks like this, right? This will be 1 over x, and for the shape corresponding to 1 over x squared, it's really very similar, except that it's basically faster decreasing, right? It's going to be like that. But in both cases, the shape that I'm trying to compute its area is infinite in the sense that it's not going to be closed to the right side. That gets, moves to the right hand side indefinitely. So a naive answer to this, well, it'd be, well, it's the area is infinity, right? Because you keep on adding stuff, right? This is an infinite surface. It's never closed. So, the area should be infinity because it never ends. You keep on adding positive stuff. Those stuff that you add on the right are smaller and smaller, but they're still positive and they never stop essentially, okay? Because the graph will never touch its asymptote. But see, that's the problem with infinity. What does it mean in the after all to compute the area of an infinite surface? There is no such thing unless we define it in a mathematical way. If I tell you that the area is infinity, I really say absolutely nothing, because it can mean whatever I imagine it to mean, right? I mean, it's without a precise definition. So hopefully for calculus and in real analysis in general, the notion of a limit comes to rescue. To give a precise answer to this question, what this area is, begs the question, what is the integral from 1 to infinity of each of these functions? So basically we need to come up with a definition that is satisfactory for an integral in which one bound, the upper bound in my case, is infinity. And so this leads to the definition of the Riemann integral, the improper integral of type 1, which I'll get to it on the next page. But I'm going to show you right away how you do this with this example. One way to come up with this definition is to simply take, for example, a variable to replace the infinite bound. And then after you compute the integral, you let that variable to go to infinity. So the way we're going to define and actually compute each of these improper integrals is to replace the infinity bound with a variable, let's call it b, compute that integral in the same manner you computed before, and then once you're done, you simply take the answer and find the limit as b goes to infinity. So imagine basically you stop at some point here with point b greater than 1. That becomes the definite integral in the traditional sense that you learn. But then once you find that answer, you simply let b to go to infinity and compute that limit. And if that limit exists and it's a number, we call that the improper integral, or we call that the area between the graph and the x-axis, provided that this limit exists. So essentially my discussion here suggests that in some cases that limit may exist, in some other cases it may not. And so let's do this for this quick example, because the integral will be pretty easy to compute. So in the case of f of x, that's 1 over x squared. We're going to write this as a power. So x to the minus 2 dx. And by the way, we could do this limit at the end if you don't want to carry this limit with you while you do the integral. So that's a power rule. So you have x to the minus 2 plus 1 over minus 2 plus 1 between 1 and b. So let's simplify this a little bit. X to the minus 2 plus 1 is x to the minus 1 over minus 1. That's just minus 1 over x between 1 and b. All right, we're going to plug in b. So minus 1 over b minus 1 over 1. Plug in b, plug in 1, take the difference. That gives me 1 minus 1 over b. Okay, so now as b goes to infinity, 1 over b goes to 0. So the limit is 1 minus 0, which is 1. So surprisingly, if you do this for the first time, this may seem like a surprise, although the shape is infinite in the sense that it has an infinite length, right? So for this one here, that decreases faster. Nevertheless, the area approaches 1. So the area is equal to 1, but when I say is equal to 1, is in the sense of this definition, in the sense of this limit being equal to 1. So what if we do the same thing? Let's see if I can fit it in here. For the other function, that's going to be more immediate, right? So the integral from 1 to infinity of g of x dx, that's the integral from 1 to infinity of 1 over x dx. Again, replace the infinity domain with, or the infinite domain with b. The integral of 1 over x is just ln of x between 1 and b. So this will be the limit as b goes to infinity, ln of b minus ln of 1, which is 0. However, as b goes to infinity, ln of b approaches infinity. Just remember how the graph of natural log looks like. Let's put it here in the corner, right? That's the graph of natural log. If its argument goes to infinity, the logarithm goes to infinity as well. So the first case, the area is infinite. I mean, the area doesn't exist, in other words. That's the proper way to put it, right? The area doesn't exist in this sense. I mean, it's not a real number. We will say that this integral diverges, to be more precise. We will write the definition on the next page. But let's summarize what we learned. We have shapes of infinite size, let's say, in this case an infinite length. Does the area make sense? I mean, does it even make sense to ask what the area of such shape is? Well, apparently it does, because in some cases, the area, according to this definition, via this limit, may be a real number or it may not. So it might converge or it might diverge. And with that being said, we're going to move on the second page to give a proper definition of this improper integral and then move on with some other examples. So stay tuned for the second page. So an improper integral of type 1 is one in which one or both, although I'm not going to get into this today, one or both bounds are infinite. And I'm going to limit myself today with bounds, upper bounds being plus infinity. The way to compute if the lower bound is minus infinity is really the same way. We're going to get to more examples maybe in another lesson. But type 1 means one bound essentially or both is infinite. So basically infinite intervals of integration. So by definition, if you have the integral from a to infinity of a function, this by definition is equal to the limit as b goes to infinity of the integral from a to b of f of x dx, provided this limit exists. That means it's a real number. So otherwise, we say that the integral from a to infinity of f of x dx is divergent if that limit doesn't exist. So I want you to not overcomplicate. It's an important lesson, but try not to overcomplicate it. From a computational point of view, there's not too much headache. The only difference is that infinite bound is replaced by a variable. From that point on, you're going to compute that integral with any method you want or can, right, that you learn already. The only difference is that when the time comes to plug in the upper bound, b, that's going to be a variable, not an actual number, and you will take the limit for that variable to go to infinity and then decide at that moment if your answer exists or not. So let's do another example, and just for practice, one in which we have one that requires integration by parts, just to put some variety into this. So let's say we have to compute the integral from 1 to infinity of natural log of x over x squared dx. If you don't want to carry that limit with you all the time, you can basically just replace infinity with b, do the integral, and then do the limit at the end. This requires integration by parts. Notice that if it had only over x, a u substitution would have worked, but it has x squared, so you should view this as suitable for integration by parts. I'm going to write it as the products of two functions. And remember the trick we had before when we said that for the integration by parts to work, you need to basically establish if one of these factors becomes easier if you differentiate it. And that's obviously the case for natural log of x. So I'm going to use, let's write the integration by parts formula here in this box. I'm going to use this version of the integration by parts. So if you have the integral of f times g prime, that's f times g minus the integral of f prime g. So the key thing is to identify f. What is the part of the function that gets to be easier if it becomes under the derivative via integration by parts? So that's natural log of x, which means the remaining part, you need to write it as an integral, excuse me, as a derivative. So that means you need to integrate it and write it as a derivative. So leave for now ln of x as it is. X to the minus 2, if I integrate it, that's x to the minus 2 plus 1 over minus 2 plus 1 under the derivative. So let's simplify this a little bit. X to the minus 2 plus 1 is just x to the negative 1. So that's minus x to the negative 1. And now it's in the proper form for the integration by parts. So on the outside, it's f times g, so ln of x times minus x to the negative 1, minus from the formula of by parts, and then ln of x prime minus x to the negative 1 dx. All right, so let's do some simplification. That's going to be minus ln of x over x, and then the integral ln of x prime, that's just 1 over x. Minus on the outside can be combined with the minus from the outside, that's plus another 1 over x. So then the last integral is 1 over x squared, which is x to the negative 2 dx. And then x to the minus 2 plus 1 over minus 2 plus 1. I'm going to plug in the bounds at the end. Right, all of this is between 1 and b. So let's see, it's minus x to the negative 1, which is minus 1 over x. Minus ln of x, okay, minus 1 over x. Okay. Double check one more time. All right. So this between 1 and b. And if I plug in b, that's minus ln of b over b, minus 1 over b. And if I plug in 1, that's minus ln of 1 over 1, minus 1 over 1. Let's simplify further. That's minus ln of b over b, minus 1 over b. Ln of 1 is 0, that goes away, and then plus 1. Okay. So this now has to be computed with the limit, right, as b goes to infinity. So the final answer, if the limit exists, is going to be limit as b goes to infinity, and we can put this into a single fraction maybe, ln of b plus 1 over b plus 1 on the outside. There are many ways to do this limit. When I teach calculus 1, I usually allow students basically to put the limit right away by estimating. So when you have infinity over infinity, this is an infinity over infinity case, which can be done with L'Hopital. But normally, if you remember that the limit in this case depends on the dominating terms, depending on which one grows faster to infinity, then you could tell immediately what the limit is. Usually the limit is going to be a constant, 0, or plus or minus infinity, depending on the case. For example, here I can tell right away that the limit is 0 because natural log of b, which is the dominating term on the top, grows slower to infinity than b. You know, the logarithm is slower, goes to infinity slower than a polynomial, and a polynomial is slower than an exponential. If this doesn't ring a bell, just do a quick L'Hopital with respect to b, right? So you can take ln of b plus 1 prime over b prime, and that gives you 1 over b over 1, and that goes to 0. All right, but bottom line, the limit exists and is equal to 1. So my improper integral from the beginning is convergent and is equal to 1. All right, so on the next page, we're gonna do type 2 integral, which you will see it's natural to ask about that type of integral by simply looking at a different type of shape when it comes to these infinite areas or infinite shapes whose areas can be finite or infinite. So stay tuned for the next page. Okay, so the type 2 improper integral can be compared to the same situation as before, but this infinite shape that extended horizontally to the right, what if it extends vertically, let's say upward or downward? So let's look at an example before we define it. And I should say that these type of integrals are tricky sometimes if you're not aware of them. Some of them more subtle errors that can happen in calculus come from improper integrals of type 2. But if you pay attention and really make sure you understand this, you are empowered by this type of lesson. You can make even jokes with your colleagues that don't know this and trap them basically with tricky examples that are not so obvious in the beginning. So I'll show you immediately what type of common mistakes can happen in this case. So let's say we look at this function 1 over square root of x between 0 and 4. Now notice already, if you look carefully at the domain, that I took 0 strictly less than x, because obviously the function is not defined at 0. So already we have a new type of notion that needs to be defined, because so far the Riemann integral we talked about involve functions defined on a closed interval. So if you don't pay attention, you should realize already that we didn't learn up until this point how to do this problem, because the lower bound, it's not in the domain of the function. It's not defined at that point. In fact, if we sketch this function to go back to that infinite size of a shape here, as x approaches 0 from the right hand side, there is a vertical asymptote at 0. As x approaches 0, the function goes to infinity, and then it decreases all the way up to 4, right? So we took the domain 0, 4. So it decreases up to the point 4, 2, right? When x is equal to 4, the kind of a mess here. When x is equal to 4, y equals 2. So basically, if I ask what is this integral, it's me asking what is this area. Again, just like with any Riemann integral, the area between the graph of the function and the x-axis, but notice that this shape extends upward indefinitely. So it's like the previous shape, but it doesn't extend horizontally but vertically. So it's still an infinite size shape, therefore we know already the answer. The area may or may not exist, provided that a certain limit may or may not exist. The way to compute this and figure out the answer is very similar to the previous case. Essentially, you choose a variable to replace the troublemaker, namely the point of discontinuity, or the point where the function doesn't exist, and then take the limit as that variable approaches that point. this will be a sided limit because the function is defined between 0 and 4, so we don't actually care what happens if x is less than 0. So to answer the question, what could be the integral from 0 to 4 of 1 over square root of x dx? Just like before, we're going to replace the lower bound, which is the bound where the function doesn't exist, with a variable. Let's call it a. We're going to do the integral as we normally do. And when we're done, we're going to let a, pay attention here, to approach 0 from the right-hand side. Right? It's like me taking a to be very close to a, finding that integral by classical means, but then we let a to approach 0 from the right. It has to be from the right because, again, the domain of integration is 0, 4. So it has to approach 0 from the right. I don't care, in other words, what happens if it approaches from the left. I mean, in this case, if it approaches from the left, it's not going to exist because it's square root, right? It can be a negative number, but it doesn't matter. It approaches from the right because it's the right side of the... because it comes from the right side, since the 0 is a left endpoint on the domain. So in a nutshell, we replace the discontinuity point, the bound, which is either infinite or in this case a discontinuity point, with a variable. We do the integral and then we find the limit of the answer. So let's do just like before that integral. This is purposely chosen so to be easy to integrate, right? So that's going to be a power x to the minus 1/2. And let's see, the integral x to the minus 1/2 plus 1 over minus 1/2 plus 1. This will be between a and 4. So let's simplify it a little bit. 1 to the minus 1/2, that's going to be 1/2, and then 2 in front of it. 2x to the 1/2 between a and 4. Again, if you don't want to carry the limit with you, you could do this at the end after you're done with the integral. So now let's plug in 4. 2 square root of 4, we can go back to the radical, minus 2 square root of a. And then 2 times 2, that's 4 minus 2 square root of a. As a approaches 0 from the right, notice this goes to 0. So the limit is equal to 4. So the integral is convergent and is equal to 4. And that's one example of a convergent improper integral of type 2. And before I write the definition, it's not much of, I mean, we know already how to do this, these examples, but just to put side by side another example in which the integral will diverge, let's do it now. So another example, let's say we have to compute the integral from 0 to 1, 1 over x minus 1 squared. Now I want you to pay attention here and notice that the troublemaker point is actually 1. So the upper bound is the one that makes the integral improper, because the function is not defined at 1. So the vertical asymptote is at x equals 1 on the right side of the domain. In this case, this point is replaced by a variable. So it's going to be the integral from 0 to b, 1 over x minus 1 squared dx. And notice here, pay attention, the limit will be as b approaches 1 from the left, because one more time, the domain of this function is 0 and 1. The function is not defined at 1, so therefore to come up with the integral from 0 to 1, we take that variable b so that we can have a closed interval. So this b is chosen to the left of 1. We do the integral, but then we have to let b to approach 1 from the left side, because now the discontinuity point it's on the right hand side. It's a u substitution, but it's a mental one, right? X minus 1 is just like x. So the the integral of 1 over x minus 1 is going to be minus 1 over x minus 1. You could do it in more than one step using the power rule for the integral. And let's see, we plug in now b first, and then 0. All right, so make sure you go slow and pause if you need to catch up. This part here is minus 1 eventually, right? But this part, if you take it separately, this is like 1 over 1 minus b. As b approaches 1 from the left, this is going to be 0. So b is less than 1. This is going to be like 1 over something that goes to 0 but positive, which is plus infinity. So, in other words, this approaches infinity as a limit, so it goes to infinity. So that means the area doesn't exist in the sense of our definition. So the integral is divergent. All right, so I'm going to write down the main definition of, I'm going to write down all the types of improper integrals that you may have, and some others that we still didn't cover yet, that appear maybe less often, and continue with more examples, and also the one that I promised you, which shows you how you can end up with subtle errors if you don't pay attention. So stay tuned for the next page. Okay, so basically we have for now two types of type 2 improper integrals. There is a third type, which I'll show you immediately. But let's actually review the two ways in which you can have these, the ones corresponding to the previous three examples. So let's say the function f of x is defined on an interval a and b, and let's say that f of x has an infinite discontinuity at x equals b. In that case, if you want to compute the integral from a to b of f of x dx, then you replace the point of discontinuity, b in this case, with a variable, let's call it c. Compute the integral, and then you let the limit of the answer as c approaches b from the left side. So that was the previous example, basically. Let's say f of x has an infinite discontinuity at the lower bound at x equals a, then the integral from a to b of f of x dx is evaluated by replacing the lower bound with a variable, let's say it's c, and then letting the limit as c approaches a from the right hand side. That was my first example of type 2. So the interesting example, what happens if the discontinuity happens in the middle? So what if, for example, f of x has an infinite discontinuity at x equals c, which is a point between c and b, between the domain of integration. So what do you do in that case if you want to, so that's one type, second type. So what if you want to compute still in that case the integral from a to b of f of x dx? So this is the one that sometimes is tricky, because if you don't pay attention, you may not notice that the function has that discontinuity somewhere in the middle of the interval ab. It can be defined, well, and continuous at a and b, but not in the middle. I mean, at the interior point between a and b. In that case, the definition of this improper interval depends on whether the following improper integral exists. So you simply break down the integral between a and c and c and b. So this is going to be the integral from a to c of f of x dx, which is itself improper, plus the integral from c to b of f of x dx, provided both converge. So provided that both of them converge, then this is how we define the integral in this case. So here's an example, and then I'm going to show you how people can miss this and end up with errors or mistakes. So let's say I want to compute the integral from 1 to 2. No, excuse me, the integral from minus 1 to 2 of 1 over x squared dx. Now notice the interval of integration is minus 1 and 2. But x equals 0 belongs to this interval minus 1 and 2. If I were to sketch the function, there's a vertical asymptote at 0. So if x is minus 1, y is minus 1, and then the function increases all the way up to infinity like that. And then to the right of 0, it decreases from plus infinity all the way down to 2 and 1 over 4, right? So if x is 2, this is 1 all the way up to 1 over 4 here. So what I'm asking is essentially this area. It's an infinite area, but now the vertical asymptote is in the interior of the interval of integration. So this will be convergent provided that the first piece is convergent. So you must essentially break it down over that point of discontinuity, which is x equals 0 in this case. So between minus 1 and 0, 1 over x squared dx, plus the integral from 0 to 2, 1 over x squared dx. Each of them is improper in the sense that we established before, the first two types. So for the first one, we're going to take the limit as b goes to 0 from the left side. From the left of 0, because it's less than 0 in that case, of the integral from minus 1 to b, x to the negative 2 dx. And for the second one, we're going to let limit as a goes to 0 from the right side, the integral from a to 2, x to the minus 2 dx. So if one of them diverges, you don't need to do the other one. We're going to do both of them just to see how it goes. But if one diverges, then by definition, the original integral is divergent. So the first piece is x to the minus 2 plus 1. That's going to be minus 1 over x, the antiderivative, evaluated between minus 1 and b. And the second one, obviously same function, minus 1 over x, evaluated between a and 2. So the first one is minus 1 over b, let's see, minus 1 eventually, because with a limit here as b goes to 0 minus. And then the second piece, it's minus 1 over 2 minus 1 over a, which is plus 1 over a. In any case, both of them diverge. As a goes to 0 plus, this piece goes to infinity. This goes to infinity as well, because 1 over b goes to minus infinity, but with the extra minus, this goes to infinity as well. So divergent. So the way you can make fun with people who didn't learn this before is to ask them to compute this, because the common mistake, so this is going to be wrong, but this is the common mistake. If you don't notice this is actually improper, if you don't pay attention to the function and the interval of integration, you might be tempted to simply do the antiderivative, which is minus 1 over x, plug in the bounds, and minus 1 over 2, minus 1 over minus 1, is that right? So minus 1 over 2. And then incorrectly conclude basically that minus 1 over x between 2 and minus 1. 1 second. minus 1. And then incorrectly conclude that this is minus 3 over 2, which is convergent, right? I mean, the actual number, which is obviously going to be wrong. So if you don't notice that discontinuity point at 0, I just want to double check something before I move on. Yeah. Okay. So these are all the types of improper integrals of type 2, I'm sorry. And I'm going to move on to the next, I'm going to have another short piece, probably the last page before we call it a day, with some other type of improper integrals of type 1. I'm not gonna go over those, but just to be aware that they exist. Some of them are not gonna be necessary, but just for the purpose of completion of the topic before moving on. So stay tuned for the last short piece.